Dr. Daniel Scheeres is a distinguished professor of aerospace engineering at CU, specializing in astrodynamics and satellite navigation. Dr. Scheeres has also done work for JPL, the Jet Propulsion Laboratory, and received rewards from NASA for his group's work on an asteroid redirect mission concept. He is the recipient of numerous awards for publications on astrodynamics. In fact, he is so recognized in the field that you have an asteroid named after you. Dan, that's pretty cool.
Yeah, sounds impressive.
It is. No, that's great. Thanks so much for being here with us today. And we'll jump right into our conversation with you about asteroids. I guess the first question, just to set the groundwork for everything else that I'll ask, is what is the difference between comets and asteroids? We hear a lot about these two things. What's the difference between them?
Yeah, thanks, Colin, and I'm very happy to be here in my own house, yet everywhere. So that's the new reality we live in. So yeah, that's a great question about comets and asteroids, because if you go back in time, they were really thought of as very, very different objects, because asteroids are really these little points of light, little stars that just happen to be moving, not with the planets, but sort of on their own trajectories. And but they seem like not much is happening. Can you hear my dog in the background, or is this okay?
We heard a couple of barks, but it was not covering you up at all.
Okay, all right. Let me know if it gets too loud.
Absolutely.
So, yeah, asteroids are just these points of light that people saw, and they realized that they had to be inside of the solar system because they were in orbit around the sun, but they seemed like sort of dead, lifeless things. Okay, just something reflecting the light. Comets, on the other hand, and asteroids have only been known for a few hundred years, really. Comets, on the other hand, are these celestial phenomena where you see, not just a point of light, but this huge cloud, and depending on how close it comes to the Earth, it can subtend a large angle in the sky. And going back millennia, these things were, omens and predictors of doom and destruction and all this sort of stuff. So when you just step back in time a bit, and then really even a few decades back in time, our sort of concept of asteroids and comets as two different types of bodies was, yeah, it was very, very profound. One is, by a few decades ago, we knew that the comets were expelling gas, and they had volatiles and liquid water or ice on them, and they got close to the sun, and they just sort of heated up and boiled away. Whereas asteroids, we thought, well, they're just rocks, okay, and just rocks going around the sun. Nothing, they're interesting, but nothing dramatic like a comet was going on. But really, over the last 10 years or so, there's been a really strong transition. And while there's still things that we definitely call asteroids and definitely call comets because they have these characteristics, as we've had more scientific missions, space missions to comets and to asteroids, and got really have, and as we've gotten close-up images of them and improved our astronomical techniques so that we can see, further and fainter and deeper, we've started to discover that there actually seems to be a continuum of bodies going from asteroids all the way to comets. And that's sort of interesting because it's like you see these two, tent poles in the distance. As you get closer, you realize that it's part of one whole structure. And that structure is really just primitive bodies in the solar system. And what we now, really the way that we think about asteroids and comets now is that they're really all representative of primitive bodies that are leftovers from the formation of the solar system. all in orbit, you know, in their own peculiar orbits and regions around the sun. And then as you study them closer and closer, you can see that, you know, some of the asteroids are really rocks. And it's almost as if, or in fact, we believe that they maybe used to be part of a protoplanet, where that protoplanet was heated up and it melted this primordial stuff and then compressed it and made it into a rock. It's like we have rocks right in our backyard. But then as you go along that continuum, you have materials that haven't been quite as processed. You know, they're more pristine. Maybe they never were in the interior of a protoplanet before it hit another protoplanet and shattered. So it's you know, it's a more faithful remnant or representation of what used to be and what initially was in the solar system. And as you keep on going across that continuum, at some point you also get to bodies that not only they've never, you know, they may never have been in the interior of a body and highly processed, but they've never been that close to the sun. So that they've never been heated up very much either. And so as you go more, and it's not more and more primitive, it's more like what, you know, what processes have acted on these very old bits of material. And as we go usually further out in the solar system, they've been not subjected to such high heating, and they're more what we usually think of as pristine, in that they retain more material from the formation of the solar system. And you can sort of trace these families all the way through the solar system, these bodies all the way through the solar system, until you get out into the Kuiper Belt, where you have extremely primitive materials that, you know, have only seen the sun as a little speck of light in the distance. They're quite cold, you know, and you just think about the Pluto flyby images, you know, bodies like that. That, you know, they have their own mechanics, they have their own seasons and the like, but they're very different. And the material that they have is very primordial, hasn't really been changed much since the formation of the solar system. And what happens with comets is occasionally these bodies that are very far away from the sun, because of gravitational attractions and this and that, they sort of get bumped into an orbit that maybe gets them a little bit close to Jupiter, or they, what we say, get resonant with Jupiter, so that Jupiter starts to kick them around, bully them a little bit and all that.
With its gravity, they're not actually running into Jupiter, right? It's gravitational interaction.
That's right. That's right.
Okay.
Distant gravitational interactions. And eventually, yeah, that can move these primordial, you know, never been heated bodies that are far out in the solar system, move them into orbits when they actually start going into the inner solar system. And so that's when we, you know, and that's what we call a comet then. Because as soon as it starts heating up, suddenly you have all this ice that's been there for billions of years boiling away and making these big dust clouds and, you know, these fantastic scenes that we can see at night. So that's sort of a long answer to your good short question.
No, it's interesting that there's actually a lot more to unpack there than I think I was anticipating, in that there's, even as an astronomy student, it still hasn't really like made its way through my head that they're not necessarily these distinct objects, that there are asteroids and then there are comets, and that they are totally separate. It sounds like, I mean, you know, is it true that if, you know, we were to look at some object, that it, you know, some primitive object in our solar system that's not a planet, it's, you know, that's some small rocky thing, do scientists objectively and definitively classify it as one or the other? Or is it kind of this spectrum from like asteroid likeness to comet likeness?
So right now, I think the field, you know, still, I mean, the field is always at several different levels, and you have the people in the front lines who are like, I can't call this a comet, but I can call it an asteroid, and, you know, it's something different. And then all the way into the back lines where, you know, well, we have to name it. Well, what is it? Is it an asteroid or a comet? And when you go all the way into the back backlines that, that science is evolving, and, they catch up, but they don't want to be too fast about it, because what if
Sure.
you say, oh, I found a different type of body, and they come up with the whole naming convention, and you're wrong, right?
No.
Yeah, yeah.
Kind of like what we have with the dwarf planets and Pluto, and is it a planet, is it not?
Right.
That sort of thing.
Yeah, yeah, and so you see that the time scale for these conversations too can be, decades long. We find this body. Oh, it's a planet. Vesta, or no, not Vesta, but Scheeres. That was a planet for a while, right? Then they realized, well, it's kind of small, maybe not. Yeah. So this happens all the time. So right now there's actually 3 types of objects that we now have: asteroids, comets, and interplanetary bodies.
I was actually just about to ask, is there a 3rd category that we should introduce into the vernacular of talking about stuff in space?
Yeah. So these interplanetary interlopers that we've seen the last year or two, that is now a new class of body. But these are the official names. When you really get into the current ongoing science, we then, of course, have additional names that we use to distinguish between them, because we can have dead comets or dormant comets, bodies that we think are comets that in the past were spraying out all their gas, but they ran out of gas, or they got covered by dust or something, so that they're no longer active. We can have active comets. We can have active asteroids, which are asteroids where we see like the release of a lot of dust, and we see this astronomically, but we're pretty sure that it's not gas, that it's not a bunch of ice that's being, sublimated off the surface, that it's actually something happened on that asteroid.
Okay.
That hit another asteroid, or it got spun up really fast by the Yorp effect, which we could talk about if you want.
Okay.
And this sort of fell apart and shed a lot of material. So when you want to start to call a body based on its activity, suddenly our definitions are getting a little bit stranger. Right. And then we have really another class of active asteroid with the OSIRIS-REx mission to the asteroid Bennu. That's a mission that I'm a co-I on. I'm involved with a team of hundreds. Okay.
Sure.
But that particular asteroid, we actually, when we got there, we actually started seeing small centimeter-sized bits of what we call ejecta or particles being ejected from its surface. And they would get ejected up, some would escape, some would just fall back down again, some would go into orbit for a few days before they fall down again. And that's a level of activity that we never expected, and which we could have never seen from the Earth. It's like if you're standing on Bennu, which is only like 500 meters across, so think, a lesser foothill along the Front Range. Right. If you're standing on there, and if you're like throwing little, centimeter-sized bits of rock every couple minutes, how are you going to see that unless you're right there and almost getting hit by those rocks? Right?
Seriously.
Yeah. So that's yet another classification. And we think it may be special to Bennu because Bennu is a very primitive asteroid. It doesn't have ice anymore because it's been heated up enough to get rid of the ice, but it hasn't been, sort of crunched in the interior of a protoplanet. So so we start to wonder, what is the dividing line? If you took a hunk of comet, a hunk of asteroid, a hunk of a primitive body like Bennu, and you start to compare them, what are the differences? And maybe it's all similar material. It's just been through the ringer or not through the ringer. So
sure. Well, yeah, I guess, if we're talking about that, we could trace everything back to, it's really everything really is just quarks. And, there's the ways that they've assembled into other stuff. But it's interesting that this classification is a lot more kind of dynamic and mysterious than at least I was kind of raised to believe that something is either one or the other, and that was that, and you moved on.
Yeah, and that's really the activity of science moving forward. I mean, I think in almost any field, as you improve your microscopes, so to speak, as you can zoom in a little bit closer to whatever it is you're studying, you have all these theories about how things are going to happen, and you use that to motivate the money to build the microscope so that you can take a close look. And whenever you look, it's usually not exactly what you expected, and you uncover new things. And we've gone through a few decade phase of pretty large investment by NASA, the U.S. government, ESA, Japanese, Chinese now, Russians, into studying astronomical objects, into space objects. And every time we get new scientific data that sort of zooms in more and more, we're discovering all of these new things. And so it's a very exciting time to be involved in this field.
Sounds like. So I know, like you said, there's not distinct classifications per se, but we do kind of see sort of reservoirs of where these things exist. Some are in one area of the solar system, some are in other areas of the solar system. Where are these sort of general areas where we find these different kinds of bodies?
Yeah, again, that's a great question. And if you go back to elementary school, I guess, and you learn about the asteroid belt, right? The main belt of asteroids. It's between Mars and Jupiter. And even inside of the asteroid belt, as you go from a little bit closer in towards Mars to a little bit farther out towards Jupiter, you actually get, on average, a change in the properties of the asteroids, where the ones that are a little closer in tend to be a little rockier, maybe a little more processed, definitely don't have their ices anymore and all that. And as you go further out, they become maybe a bit more primitive, maybe haven't, been captured in the interior of a protoplanet, maybe just on the surface of one. So even in the main asteroid belt, you have some differentiation, some differences of this material as you go further and further out.
So just for perspective, like how wide is the asteroid belt? Does it expand through that whole distance between Mars and Jupiter, or is it more confined than that?
Wow. You want a number?
Not necessarily a number per se.
I want a number down to the millimeter. I want those bounds down to the millimeter from Mars to Jupiter.
Let me Google that for a second.
Yeah, right.
No, I mean, I've seen the pictures many times, but it's and in the solar system, we tend to use units of an astronomical unit, okay, which is the distance from the sun to the Earth. And Mars is about 1.5 astronomical units away from the sun. And I think as you get out to like 2 astronomical units out through, I'm thinking 3 or 4, that's where the majority of the asteroid belt is. And it's not like Star Wars. Okay, remember Star Wars, you fly into the asteroid, oh no, all these asteroids are crunching next to each other. That's more like a ring, okay? I think if you flew into Saturn's rings, maybe you would see that. Okay, but yeah, there's lots of asteroids in the asteroid belt. But if you're sitting on one asteroid, you're not going to see any other asteroids around you because they're pretty sparse, and they do hit each other, but it's not but it's a relatively infrequent occurrence that they actually run into each other. So yeah, that's sort of the dimension of the main belt. Now, as you keep on going out, the next thing you get to really are what are called the Trojan asteroids. And these are asteroids that are at the same distance from the sun as Jupiter, but they're in this special location. They're like 60 degrees ahead or behind of Jupiter. And they're sort of trapped there by a combination of Jupiter's gravity, the sun's gravity, and just their orbital motion around the solar system. It turns out that there are some theories now that those are actually very different type of body that were trapped there very early on in the solar system. So I'm not going to dig too much more into that. But what we do believe is that those Trojan asteroids are actually quite primitive. And when I say primitive or pristine, what I really mean is they have a lot of ice left. So if you took one of those guys, brought it into the inner solar system, it would, give you a nice light show and lots of ice and sublimation.
But we're calling those asteroids.
Yeah, well, they're called asteroids because we don't see them sublimate. We don't see them have these comas and all that, but they are quite primitive objects.
So a comet is not just an icy asteroid. There's more. Or an asteroid is not just rock. It can also have water on it. The water does not make it one or the other.
That is true. In fact, really coming back to this classification, what makes a comet, what makes an asteroid? If you go by an observational perspective, a comet is something that has a coma, that you see gas coming off of it and spewing out as it goes through its orbit around the sun. An asteroid is a point of light that doesn't have this activity. And where things have become confusing is that we have comets that actually stop being active. Like, we see a comet, maybe 50 years ago, it came through, it had some coma and all that, and we can track it, and it comes through again, we don't see anything, all right? Is this a comet? I mean, should we change the name?
Does the comet become an asteroid?
Yeah, or we've had asteroids that suddenly have had this huge, outburst of, from spinning up or from being impacted, but technically it should be a comet because it has this coma that we see.
Huh.
In fact, there are examples of asteroids that have comet names or comet designations because they first saw something that was breaking up. It looked like a comet, lots of activity. They went back, they studied it more, and they realized, oh, that was just an asteroid, okay? And it just went through this process of falling apart or something else. So, yeah, it's a very fluid naming situation, if you will, okay?
Very interesting. It's much more complex than I really ever thought that it would be.
Yeah.
I did want to ask though, we've got the main asteroid belt, we've got those Trojans, and we talked last week with Dr. Bagenal about the Kuiper belt and all the stuff that's way out there. Do we ever see any extrasolar asteroids? I know we had Oumuamua that came through our solar system real quick a year or so ago. Do we see more of those, or I think it's probably really hard to see see asteroids around another star like we do with exoplanets or something like that.
Well, yeah, so good multi-level question there. So in terms of these interstellar interlopers, I think we have definitely two that I know of. Maybe there's some additional ones. They don't make the press. It's not my area, and the press isn't. After the first couple, people don't cover it as much. But those have only been seen quite recently. The Oumuamua and I think Borisov was another one that occurred within the last year or so. And I believe both of those had some. Well, Oumuamua was interesting because I don't think they saw a coma at all. Yet they were able to very precisely track its orbit. And from that, they were able to tell that it was emitting gas. Because when a comet emits gas, it gives it it's like a little jet on it. And it changes its orbit a little. And they were actually able to tell that, we didn't see anything, but something was coming off the surface. So it was jetting this Oumuamua, and it was basically accelerating it as it went through our solar system. This is why some people say, oh, it's an alien craft. But that doesn't really hold water. It was an object that was really sublimating from its surface. So this is another classification quandary, right? We didn't see anything. It looked like an asteroid, say. Yet we know that it was primitive. We could tell it was primitive from the other sort of astronomical observations of it. And it was obviously losing material. We just couldn't see it because it was being jetted along. And there, I guess they threw up their hands and said, well, we don't have to worry about it. We'll just make a whole new classification, interstellar. So that solved that problem.
So when we talk, oh, sorry, go ahead.
Yeah, and then getting to your other question about can we see asteroids or small bodies, comets, or interstellar interlopers around other star systems? And the answer is yes and no. So we can't, resolve a small asteroid around a distant solar system. Okay, so some of the techniques we have, they can actually start to, to see or have some real constraints on planets and sizes and all that. These primitive bodies tend to be very small because they are sort of this detritus, this leftover from the formation. But, and we all know this, if you get enough dust together, if you get enough of these small bodies together, especially if they're very densely packed, you can see that because you see the light scattering from all the smaller particles. This is why we can see Saturn's rings. The individual bodies are tiny. We can't resolve them, but all that light is being scattered. And so there are observations of extrasolar systems where they can say, yeah, okay, this looks like it's a comet belt. This looks like it's an asteroid belt that's, getting ground up. And they can actually refine these techniques even more and say, well, we see this type of light being absorbed. We think, therefore, that there's, this distribution of small asteroids or dust, if you will, around the star absorbing all this material or absorbing that radiation.
That is so cool.
Assuming that we could resolve, or infer the existence of asteroid and comet-like bodies, but around other stars, would we just call them exoasteroids and exocomets, or would they have some other way that we refer to them? What do you think about that?
Man, I don't know. It would probably follow the planetary guidelines, but I don't even understand what the planetary guidelines are. So my whole career, I've sort of been stuck in the mud in our own solar system.
Sure, right.
Get outside of it, so to speak. But yeah, that seems like a rational approach.
Okay.
Which means we're probably not doing that, right?
Right. Well, yeah. Speaking of, so, we're living here on Earth. In our solar system, this is where everything that we can see is. This is where you do, well, it sounds like all of your work. And I think that to loop Star Wars back into the conversation, because that's fun. I think that, in sci-fi especially, but just when we talk about asteroids, the question always comes up, what about Earth getting hit by asteroids? What about this idea of something, from space hitting Earth and it's huge and it causes all sorts of problems? Is like, what are we actually looking at when we kind of have these questions, or when sci-fi movies or TV shows, make this event happen? Oh, sorry. Is that silly, or what are your thoughts on the dangers of asteroids hitting the Earth?
Yeah, well, to be honest, it happens all the time, every day. Any shooting star you see is an asteroid hitting the Earth. Okay.
Okay.
Or a cometary dust particle hitting the Earth. The thing is, the smaller in size you go, the more frequently we're hit by these things. Because also, in principle, the smaller in size you go, the more bodies there are of that size. Okay, when we go to planets, there's only, 8 now? When we go into asteroids that are larger than a couple hundred kilometers, there's, a few thousands. And, as you go smaller and smaller, you get astronomical numbers of these little dust particles and all that. So they are hitting us all the time. And we also know from our own geological record and evolutionary record and the like, that occasionally larger ones hit us as well. There's lots of craters around the Earth. The only way you could form them is from an extraterrestrial, a meteor coming in and smacking the Earth, making this big hole. We have a pretty good idea of what happened to the dinosaurs. And there's even more and more very interesting research being done on that I'd never get it. The big dinosaur killing impact from a long time ago. Just more and more evidence in our geological timeline of what happened. So it definitely happened. And in fact, it's a good segue, well, not a segue, but just an aside, that there's actually other classes or other places where we find asteroids. And we talked about the main belt, Trojans, and we can go out into the Kuiper belt and beyond. There's also a class of asteroids called near-Earth asteroids. Or if you want to include comets, we call them near-Earth objects, because they could be comets or asteroids. We don't always know which. And these are bodies, small bodies, that have been, so to speak, scattered into the inner solar system. Just like comets are scattered into the inner solar system, they come close to the sun, make all this light, all this dust. That happens to asteroids a lot too. And in fact, it's this class of bodies, these near-Earth asteroids, and that loosely it's defined by bodies whose orbit goes close to or through 1 astronomical unit, meaning that there's a possibility that they could hit the Earth, okay? Because, the first requirement, if you want a celestial body to hit the Earth, it first has to somehow get to 1 AU from the sun, right? Because that's where we are all the time. So there are this other class of bodies, the NEO, that cross the Earth's orbit. And some of them, we know, come very close to the Earth's orbit. And in fact, if you have one of these internet news feeds that covers science, every month at least, big asteroid comes closer than the moon, or, pumpkin-shaped asteroid or skull-faced asteroid on Halloween, all these very cool asteroids that are always flying by us. Those are all NEOs. And if they can come that close to us, they can also hit us, okay? A lot of these, if they hit us, in fact, you hear about meteorite falls all the time. A lot of times it's not a big deal, okay? But, as you make those asteroids bigger and bigger, you would want to be further and further from where it might hit on the surface of the Earth. And in fact, there's sort of and none of these numbers are very precise, but there's sort of a rule of thumb, if you get up to asteroids that are maybe 100 meters across, like a football field size, those can actually create a lot of damage if something that big would hit the Earth. And if you hit it in the middle of a city or, some other populated area, that wouldn't be good. You're getting into something like a Tunguska size event. And I don't know if you've ever covered Tunguska on your show, but it's...
Could you summarize it really quick for us?
Yeah, about 100 years ago, in the middle of nowhere in Siberia, something blew up in the sky and flattened, I don't know how many thousands, millions of acres of forestry. And people have figured out that it was probably either a comet or an asteroid that entered in over Siberia, and actually before it actually even hit the ground, it sort of exploded in the middle of the sky, and just created this huge devastation. But no one was there, or I think there was a small handful of people that were killed by it. To take it down a step, if you remember Chelyabinsk a few years ago, that's the one in everyone's car, all those car videos, people driving around, and you see this thing coming through the sky, and then like a minute later, bam, there's a sonic wave and all the glass shatters everywhere in the city. Okay, so then that's something that's even a little bit smaller, probably several tens of meters across. And so you can sort of scale that up and you realize, yeah, the bigger and bigger these get, the bigger the destruction would be. Luckily, the bigger they get, the fewer of them there are as well. And when you get into something the size of the, what we call the dinosaur killer, you have to get up pretty large, on the order of a few kilometers across. And this sort of really a couple of decades ago, this drove a lot of activity, or started a lot of activity of us, not me personally, but the people in the community, astronomers tracking, cataloging, and really paying close attention to these near-Earth asteroids. Smaller bodies, so they're not as prestigious as a planet or Scheeres or Vesta, but they come very close to us. And traditionally they were sort of viewed as background noise, and astronomers would hate them because they would be looking at a beautiful star and this asteroid would come in front of them. But it really turned into an object of focus and study. And the whole field of near-Earth object studies has really grown over the last decade or two, and we've cataloged a lot of these things. And it's nice to say that we've cataloged all the biggest ones, larger than a couple kilometers, and none of them are going to hit the Earth anytime soon. So that's nice, right? That's a positive. But as soon as you do that, you say, well, okay, so we don't have to worry about the whole civilization, ending on Earth. What about local damage and the like? And that has actually driven Congress to encourage NASA to pursue and to study these things. And actually, a couple of years ago, NASA actually created a planetary defense office, whose sole task is actually to understand the population of these near-Earth objects and to track them, and to answer this question that we haven't had to answer yet. If we find one that has a high probability of hitting the Earth, and we know that it's going to actually create, a fair amount of damage, what do we do, right? Should we try to push it out of the way? Should we just, not be where it hits when it hits? What's the appropriate strategy for dealing with something? And it's sort of a profound question, and it's a question that really, will span centuries and millennia, right? Because, the one thing we know for sure is at some point, a larger body, maybe not large enough to have huge destruction in the next few million years, but something at least locally to create a mess, will probably be discovered, and we'll have to answer this question. What do we do with that?
As an aerospace engineer yourself that has studied these objects, are there any ideas kind of floating around or that are being explored about, well, okay, say to add to the list of things that happened in 2020, we found a very large body that is right on course to hit Earth, and we have some amount of time to figure out what we're going to do and do it. Are there any ideas right now that scientists are kind of considering and keeping in the back of their minds in case this event happens?
Yeah, there are in fact a lot of ideas
out
there. They run the gamut from maybe a little crack brain, to very practical. And yeah, we could do that. Okay. You can just think about the movies that maybe you saw growing up. Was it Deep Impact, the one with Bruce Willis? That's sort of a crackpot approach.
Okay.
But we do have studies and actually space missions that are testing out some of these ideas. Okay. About how would you nudge one of these asteroids out of the way. In general, we don't want to just obliterate them, because then it's like you turn a bullet into a shotgun bolt, right?
So now you have even more things on track to hit Earth than just the one.
Yeah, and it's not completely clear whether or not this will be bad, or, sure. So we don't want to do that. It takes a lot of energy too to actually break through. It's probably better. It's like, there's a ship, and you realize that the ship is headed for the harbor, And if you don't do something, it's going to hit the harbor. Well, what do? Well, you start early. You go out there with your little tugboat and you push on it very, and you can gradually change its trajectory until it's no longer going to hit the harbor and destroy things, and it'll go somewhere, hopefully miss everything. So we have a couple of ideas about how would we push an object out of the way, and the approaches that we would use really vary with how big the body is. And as the body gets bigger and bigger, it's harder and harder to push it out of the way. But the thing is, as it gets bigger and bigger, it's easier to see the body, so that if it were going to hit us, we would see it earlier, and we could start pushing early. If you push early, you don't have to push as hard. If it's going to hit in a week, there's really nothing you can probably do. Okay, at least with the way we have things set up now. So yeah, and probably the main ones are, I guess I can throw out three main approaches. One is if it's a larger body, what you do is you go up there and you the most effective or the sort of the highest energy density thing that we have is an atomic bomb. Okay. I'm not advocating bringing bombs in space, but if there was something big coming and, if the timing was right and all that, if you went out there and you actually, deposited that energy from the atomic bomb into that body, it would actually, you could, if it's not too large, generate enough heat off of the body and sublimation and all that stuff, so it could actually get pushed a little bit out of the way so it would miss the Earth.
Well, and that sounds like a good use for that technology, right? Because we talk about atomic bombs, and in the past, we've only really seen them used for destruction. Here, it's this, crazy science, and we're using it to save the planet. So to me, that seems like that would be a suitable use for.
Yeah. I mean, that would be much better use than how they've been used.
Right.
The other way is if it's not quite so big, essentially you just get a big heavy truck and you drive it into space and you smash into it, okay, and you push it out of the way. It's at this intersection, two things hit, bam, and you can nudge it a little bit. Actually, NASA has a mission called the DART mission that was going to actually test out this technology. They're actually going to send the spacecraft and have it run into an asteroid, a very special type of asteroid. It's a binary asteroid system. So two asteroids orbiting each other. They hit the smaller one, and from Earth, we'll be able to tell now how much were we able to push that little asteroid. And because there are some open scientific questions about how effective is it to run your garbage truck into an asteroid to push it out of the way. So that's another approach, and that's probably the most practical approach, that we could launch that now and hit an asteroid. The question is it going to be enough, right? Enough oomph. And if we can work 10, 20 years in advance, a lot of times, yeah. So if we can track them very accurately, know where they'll be in advance and when they might hit, sure, we can push these guys out of the way.
So that's something you have to see the asteroid ahead of time and then plan accordingly and say, okay, we're going to launch it from here in this direction at this time, so that they rendezvous and hit each other when is the best, when that's supposed to happen. It wouldn't be something where we just have this truck like in orbit around Earth ready to go. Or would it be something like that, where we kind of have this on reserve large mass and we just deploy it when we need to?
People have proposed that, but it's such an expensive solution, and it probably doesn't really save you much, because usually you don't need to turn it on a dime. If it's decades in the future, okay, you can take a couple years to build your spacecraft and do all that stuff. The third way, it's very elegant. It's sort of like a tractor beam, but it's a very familiar tractor beam that we all experience, which is gravity, right? Gravity is like a tractor beam, right? It attracts you to the Earth, right? So you can also take a spacecraft that's and maybe you put a big hunk of lead on it, and if you bring that hunk of lead very close to the asteroid, and if you carefully position your spacecraft so when you thrust, your propellant doesn't fall on that asteroid, you can actually gravitationally very slowly pull that asteroid along just a little bit. So it's a very precise way of moving an asteroid. It's also, it takes a long time. So you could do if the asteroid's too big, you could do this for 100 years and you'd move it, you know, like a centimeter or something like that, you know, off of its nominal path. Those are three realistic technologies that, you know, any one of those could be developed and flown with some advanced warning. Now here's, just to close the loop on this topic, this OSIRIS-REx mission I mentioned before, we're going to the asteroid Bennu. It just so happens that this asteroid Bennu is one of the most potentially hazardous asteroids now, because in a couple hundred years, it has a probability on the order of, you know, 1 in a few thousand of hitting the Earth. So, you know, you buy a lottery ticket for that, but you wouldn't necessarily worry about it. Every time I walk across the street, I probably have, you know, 1 in 100,000 chance of being hit, right? I still walk across the street. Yeah, but this particular asteroid, in a couple hundred years, its orbit evolves to the point where it has a series of close approaches to the Earth. So it's a very valid question. Is it going to hit the Earth or is it not going to hit the Earth? One of the things we're doing with the OSIRIS-REx mission is we're able to really nail down the orbit of this asteroid right now and understand all the little forces that act on it. And from that calculation, we should have a much better prediction about whether we should be worrying about it or if we can just say, no, okay, no worries, nothing to worry about. So this is far enough in the future so that we don't really need to get nervous about it now, but it is an interesting scenario. And it's something that in the next year or so, you'll definitely see some papers about this. Yeah, so it's an interesting question. Will it or won't it?
Right. Well, and I think that, you know, the situation with asteroid Bennu is kind of makes it, you know, I think that it would probably be easy for certain, you know, people to say, this is a ridiculous conversation. Why are we even talking about investing money into deflecting asteroids when when it's never going to happen? And then we see this one and we think, oh, but wait, maybe this is a thought that we should be entertaining. Really quick, because I know that you think a lot about, you know, astrodynamics and the, you know, your work, you know, kind of considers how would you move things in space and get from here to there. The last two methods that you described have a lot to do with just a large mass, either running it straight into the potentially impacting object, or, you know, gravitationally leading it in a direction that makes it not dangerous. Are we talking like enough mass that it would be a challenge to get that off the surface of the Earth? Because I know that, you know, that's a huge kind of roadblock in space travel, is if you have this really, really heavy thing, you know, it gets more and more and more expensive and difficult to get that thing off the surface of the Earth, you know, the heavier it gets. So, you know, are there technologies that we would use to make that happen? Can we do it right now, or would it require something kind of extravagant to figure out?
Yeah, so it's a great question. And again, it comes down to how big is that object that you want to push, and how far into the future are you be able to predict it's, that it might be a problem that you want to get rid of it or push it out of the way. You know, right now we can launch all three of these sorts of missions. Okay, you know, with some lead time for some of them. Okay, but I'm talking 5 years maybe. If you really needed to do it, probably less. Now, to make it more efficient, you could either try to build a bigger spacecraft. And, you know, you can sort of think of it. Let's say you want to use the garbage truck technique and just run into this stuff, okay? You could launch several garbage trucks and glue them all together and bring them out en masse to go hit the asteroid. Or, you know, or maybe you just send one at a time, and you know, each one of them just takes a shot hitting it, you know. like a bunch of little mosquitoes, you know, biting you to death or something.
Feels like a boss level in a video game. You see the health bar just kind of decreasing with each successive garbage truck hitting the asteroid.
That's right. That's right. That's right. And you know, there's some real trades there, engineering trades. It's probably at some level more efficient if you can get them all together at one bunch and smack into it. But then that means that you've got to attach them all in orbit. If you can't, if you can't launch it all in one fell swoop, you gotta pay an astronaut to, bolt these things together up in space and do all that other crazy stuff. So it gets to be very complicated. It's a very systems-oriented type of question. And there's the mechanical efficiency side of it, which is pretty easy to analyze, right? You can do that with Newton and, F equals ma and all that good stuff. And then there's like the whole system side of building these things and constructing, and do you have big enough engines to accelerate that mass? And that becomes very involved. So it is a pathway for the future. We can definitely build things in space. Just look at the space station, right? That was all bolted together. And we have a lot of expertise there, but it takes a lot of investment, a lot of time, and a lot of dollars to do it right. So there is a lot of research that goes on in this whole assembly and orbit question, and what people are really trying to figure out is how do you do it without astronauts in the loop, without having to pay someone to stand there and take their wrench and bolt everything together.
So it sounds like all space travel, any of these, kind of situations would, require quite a bit of planning and thinking and doing. It's not, something, that you can just go do kind of nonchalantly.
That's right. That's right.
Well, and one of the things that I kind of wanted to ask you about too is, we've talked about sending things into space to rendezvous and destroy these asteroids, but we're also now sending things out to take samples from these asteroids and bring them back. So we've got tons of sample return missions that are going on now. Can you tell our listeners a little bit about some of that and like what kind of things that we can learn from these sample returns?
Yeah, that's a great question. If you really think about it, we have a lot of samples of asteroids on the Earth, because every time a meteorite hits or a meteor hits, it becomes and lands on the surface of the Earth, and someone picks it up. Well, we've got a sample, right? Now, and when we look at all the samples that we have, though, we see that the sample is highly biased towards things that are tough. And it can make it through the atmosphere at several kilometers per second without completely being destroyed or burning up. So some of the initial sample missions that we've had were just to get some samples and compare it with meteorites and the like, in order to close the loop. Is what we see in space really the stuff that we're picking up off of the surface of the Earth? And some early missions really nailed that down. Yes, it is. So we were able to say, oh, okay, so we know we have space stuff on the Earth. But now we're going to we have missions to the asteroids Bennu and Ryugu. That's the target of the Japanese Hayabusa 2 mission. And the material from these asteroids generally doesn't survive going through the Earth's atmosphere. So if a little bit of Bennu entered the Earth's atmosphere as a meteor, it would probably break apart, maybe burn up, or just break apart, become little dust, which we can't then track and pick up and all that, and just settle down to the surface of the Earth because it's so weak, so fragile, so primitive. And we think the same thing is true with comets as well. They tend to be less strong. They're very porous. So that when we have, small bits of comets and the like entering the Earth, they tend to become little particles, dust particles, and they sort of gently float down. So with our sample missions that we're doing now, we're actually trying to get material that we don't see on the surface of the Earth because it gets filtered out. So either very primitive asteroids that haven't gone through the strengthening process of being inside the inner core of a larger protoplanet, or cometary bodies where there's just a bunch of ice in the like that's never been heated up. You know, if you bring that comet to 1AU so they can hit the Earth, by the time it gets to 1AU, it's spewing all of its stuff out all over the place and really changing and going through a transformation. So there's a lot of there's a big wish for comet sample return. We don't have any missions to do that right now, but it's a perennial mission of interest that gets proposed again and again. And right now we do have these missions to these primitive bodies. And once we get that material back and in the lab, it's really going to give us a lot of insight into what these asteroids are truly made out of, and then also give us insight into what the early chemistry of the solar system was, what was going on 4 billion years ago.
Well, and then I have to follow that up by asking the second question that we always get. Once we know what's on these asteroids, how practical is it for us to go and try to mine this material and make use of that? Is that a thing that we should even be considering? Are there all sorts of other implications to this sort of process that we need to worry about?
Yeah, that's a fascinating question, and you know, I've read many science fiction books about it, right? But
Yeah.
how real is it? How real could it be? And there are some aspects of it that could you know, that do make sense. I don't think our infrastructure is there yet for us to really make it practical to go and get materials from an asteroid. But when you really do a cost-benefit analysis, what actually turned out to be, you know, maybe the most valuable thing on these asteroids is this plain old water. And if you think about it, you know, if you can somehow extract water out of an asteroid, and some of these primitive asteroids should have a fair amount of water in them, not lakes or anything like that, but just in their chemistry, and you might be able to sort of fractionate it and pull out that material. Once you have water, if you have energy, you can separate it into hydrogen and oxygen. And then if you want to use it as a thruster, you can then combine the hydrogen and oxygen, you know, get or somehow use that as a propellant to start pushing yourself around the solar system. So there are materials that we could use as resources in space. There's also a big drive to figure out how easily accessible the water on the moon is. Because it has been documented that there is water somewhere up in the poles. They don't really understand how that's distributed around, you know, what chemical form it's in and all that. But if, you know, if you can access that, then suddenly you have, you know, even if the astronauts can't drink it, they can use it to actually, you know, create other materials, or, you know, make a water shield to protect yourself against cosmic rays, because water is a pretty good insulator there. So there are a lot of uses for this material, but the first step is actually documenting that it's there and that it's accessible. Okay, and in some sense, these missions, the sample return missions, missions to the North Pole of the Moon. Listen, I actually, one of the poles of the Moon, I don't know the moon yet. You know, what they're doing is they're sort of scoping out the situation. Are these resources that we can actually somewhat easily access? If the answer is yes, you know, then it really makes sense to start developing or thinking about how might you get that material. You know, is it of any use to you at the asteroid, or you know, what would make it economically viable, and then you can go down that whole path. There are companies that are thinking about these things, but I don't think, and I might be proven wrong, and it'd be great if I were, I don't think anyone's going to launch a mining mission to an asteroid anytime soon. But there certainly are groups of people that are thinking far into the future and starting to figure out, you know, what can we do now to make this a reality in the future.
Yeah. And my sci-fi oriented brain automatically goes to like when we have colonies on Mars, they're going to be that much closer to the asteroid belt, and maybe they can get water from asteroids and things like that.
Could be. I think if we're gonna have colonies on Mars, they'll have to get something out of Mars too.
Probably.
And yeah, some sort of resource extraction and all that. But yeah, it's it's always intellectually interesting to think about these futuristic scenarios. And we know that it'll never be the way we imagine it, but that doesn't mean that it's not going to be. Are we just imagining it incorrectly, or will we, will you be the one who actually has the insight that figures out, well, no, this is the way we could do it, right?
That would be the mother of all disappointments, to show up to that asteroid, thinking one thing, and you've put all this work into a mission and the money and resources to get there, and then you're like, wow, we could not have been more wrong, and then you have to deal with that. But initially, I unmuted myself to chime in earlier. I know that one of your favorite things is Mars's moon Phobos, and I've heard a lot of ideas, not formally, but about the idea of using Phobos as this kind of launch pad, or either of Mars's moons as this launch pad between some Mars civilization, and then you can, have this like midway point on one of Mars's moons, super lightweight, so you can leave and kind of move around it easily as this like dock, station to the asteroid belt. And I just think that scenario in my head is very like sci-fi and kind of inspirational, that you have, now we're on Mars and we're doing cool things on Mars, and then you have Mars's moons, and Mars's moons are like this gateway to the asteroid belt, and that's where the next like industrial boom happens, is everyone's like going to the asteroid belt to get their resources or whatever.
Yeah, I mean, the Martian moons, Phobos and Deimos, are unique opportunities, I think. What's sort of a fun thing to do is imagine if the Earth, we have our own moon, that's great, but it's kind of far away, and it's big and it's heavy. What if we had like a Deimos or Phobos in orbit around the Earth at about the same distance? We could regularly launch up there. We could have roller coasters on there. We could, we could really take advantage of it. And the idea of using, like, say, Phobos as a sort of a way station or a depot, if you will, or what have you, to access the surface of Mars is just a great idea, I think, and fascinating.
As an astrodynamicist and celestial mechanic, I hope those are right things to call you. I'll go with it because they sound cool. What is the likelihood that we could put a moon in orbit around Earth, like one that you're describing? Say we want this small moon that's right there that we can build a theme park on. Say in the future, that's a business opportunity. What are we looking at to create a moon and put it in orbit around Earth? Is that even plausible?
Well, at one level, we do it all the time.
Oh, okay. Fair.
You think of all the satellites, and even the space station, which is getting pretty large. It's not as large as Phobos, okay? But so we are doing this now. And you can imagine taking the space station, maybe you wrap it in some, material so you can like clamber over the surface or something. For us to make something big enough for it to have its own gravity so that you can start to be held to it, that would be a lot of launches, okay, with lots of rocks. People have looked at the possibility of capturing, because we have some of these NEOs. Occasionally, they fly by the Earth very slowly, and they can even naturally get captured into orbit around the Earth-Moon system, maybe for a number of years even, before then they sort of drift off again in orbit around the sun. And people have looked at it. In fact, I was author on one paper where we just did this sort of a toy study. What would it take if you had this one particular one of these very close, slow flyby, small asteroids? What's the possibility of actually getting this captured into an orbit where it would actually stay there for a while? And it's not physically infeasible. It doesn't mean that we're going to do it anytime soon. It would take lots of money Okay, and some luck as well, just in terms of timing and finding the right thing and all that sort of stuff. But you know, to capture a 100-meter rock or a couple 100-meter rock in orbit is definitely feasible. Now, getting it down into a low Earth orbit, that gets a little harder. And if you want to catch something like Phobos, which is kilometers, several kilometers across, and to stop it, capture it, and getting it to Earth orbit, you know, mechanically, sure, you can write the equations and say, oh yeah, we just need, you know, this much money so that I can buy all my equipment to
Easy.
start. Yeah, but yeah. So as you get into something interesting, Phobos size interesting, it's not really plausible. But you know, if you're getting into something smaller and smaller and smaller, it gets more and more plausible. And in fact, you know, to the point where the astronauts could put a bunch of rocks in their pockets and bring them back to the Earth, and we could launch any one of those rocks in orbit around the Earth.
Science.
Yes.
So talking about the work that you do, I was looking through your CV before, you know, as we were kind of preparing ideas for this interview, and something that you listed as one of your interests is space, and I'm quoting your CV here, space situational awareness. Can you just kind of tell us what that means and elaborate on the idea of space situational awareness?
Yeah. So this is a different, you know, we've been talking about the asteroid belt around the sun and understanding and studying all these little small bodies, okay? Well, the Earth has its own quote unquote asteroid belt, but it's all this detritus and debris that in active and inactive satellites that we have introduced into the system. So the SSA, Space Situational Awareness, it's sort of a military-ish acronym that they developed for, because the military has a lot of satellites up in orbit. They want to know what's going to hit us, or is there junk that's going to smack into us, or, oh, this is a new satellite we've never seen before. How do we figure out its orbit? Where is it going? And all that sort of stuff. And it sort of evolved into a larger field. And so we still use this acronym SSA, where it's really just the study of objects in orbit about the Earth. And how do we deal with the orbit debris population? If you saw Gravity, you know that these things can shred a space station, right? If you're unlucky, very, very, very unlucky. Okay, and we can ask the same questions in orbit that we were asking about asteroids. Well, if we have this big, defunct satellite that no one can control, and we see that over time it might smack into the space station, what do we do? Well, we can actually go rendezvous with that defunct satellite, and maybe just force it down into the atmosphere where it will burn up. So we can take a lot of the sort of similar sorts of questions that we can bring to the asteroid belt, the near-Earth asteroids and all that, and bring it up into our own place, where we've sort of dirtied our own waters, okay? But we have the ability to clean them too, and to understand what's going on there as well. So space situational awareness is sort of a shorthand for figuring out how do we track objects in Earth orbit, what can we learn from them scientifically. There are some interesting examples there, and how do we mitigate potential impacts between objects. Should we be up there sort of disposing of old satellites, or putting them into graveyard orbits, or things, interesting things like that.
So it sounds like we're really being aware of our situation in space. I could not have been more wrong in the way that I was thinking about that. When I read that, I thought, oh, it's like if you're an astronaut in the ISS, it's disorienting because there's no down, there's no gravity, in the sense of you're not being, So when I saw that, I was like, oh, he's studying how can you make sense of your surroundings? How can you as an individual have situational awareness in space? So yeah, thanks for
it's a little bit a little bit
higher order. And then, so like we, talked about right when we introduced you, you have an asteroid named after you. What does it take? Imagine one of our listeners says, I'd like to do that. That sounds like a fun course of action to do, is to have an asteroid named after me. What does it take? How did you end up having this asteroid named after you? What that whole thing look like?
Yeah, so I can sort of sketch it out. And I should say, sometimes I go to meetings where maybe I'm the only person in that whole room that has an asteroid named after me. I go to other meetings where 2/3 to 3/4 of the people in the room have asteroids named after. So it's depending on who you're with, it's impressive or it's like, oh yeah, okay. It turns out that, and this is not true for all celestial bodies, but whoever discovers an asteroid actually has rights to name that asteroid. Okay, so I've never discovered an asteroid. I hardly know at the end of one end of the telescope from the other. The people that do discover asteroids, they tend to discover a lot of asteroids, hundreds to thousands, even in a year or so. But they have the right to name their asteroids. And actually, that right expires after like 10 years, so anyone can name it, et cetera, et cetera. But usually, almost always, the discoverer of the asteroid is in the loop. Now, the last thing person that discovers a lot of asteroids is not discovering them to name them all. Okay, they're discovering them for the science, for the astronomy and all that. So what happens is, but they encourage people to look around the community. And here, this is why you mostly find people that study small bodies, asteroids, comets, and also other astronomical objects have these things named after them. So they encourage the people that they work with to look at the community and say, find someone that's done some good work that could deserve some recognition and propose naming the asteroid after them. And it's not just as simple as that, because once you have a proposal to name an asteroid after someone, you then have to send it off to the International Astronomical Union, and they have to approve it. And it's like, no pets, no political figures, no religious, there's a number of restrictions, and no felons or et cetera, et cetera, et cetera. So it does go through a vetting process. So you can't just make up names or try to buy a name either. That would also be kicked out.
That makes me think of when William Herschel, I think it was William Herschel, first observed what is now Uranus and wanted to name it after King George because that was his benefactor, and said, well, I'd like to name this planet George because George is great. And all the astronomers said, maybe we shouldn't name it George because that would be weird if it was, we go Earth, Mars, Jupiter, Saturn, George, and then now Neptune. And, that kind of doesn't fit. So it's cool that they, there's this process.
Yeah. No, it is a very similar vibe to that, and so that's sort of the process. And I was fortunate. One of my mentors, it's been like almost 30 years ago, or probably 25. Was kind enough to put me up to have an asteroid named after me, and went through. And yes, so I've proudly said that ever since. I've started to understand how the process works, and I've had a couple of colleagues where I've actually gone through that whole process of, identifying them, writing up a justification, contacting the astronomer, proposing a name, and it's it's a great honor. I mean, it's very low key. When it's announced, it's usually at a small conference, and everyone gets around and says, you've got an asteroid named after you. Like, get back to work. But it is a unique aspect of the community, that's for sure.
What is the name? We haven't said the name yet. What's the name of the asteroid that your name is attached to?
Oh, it's Scheeres.
Oh, it's just Scheeres. Asteroid Scheeres. That's it.
Scheeres, yes.
Oh, nice. That's very cool.
Number 778 Scheeres.
Got it.
Every asteroid that is documented, which means that they've seen it a couple of orbits around the sun, has a number. So mine is 7,778. We're actually up into the, I think, many tens of thousands, if not more, of asteroids now. Yeah, and it has my name. So,
Very cool. Well, congratulations for having an asteroid named after you. That's kind of neat.
thank you. Thank you. It's fun, and we try to spread the word. So there's
Well,
lots of asteroids out there.
yeah. And you mentioned kind of doing the work as part of the prerequisite for this whole thing. And one of the things that we always like to ask our guests is, can you tell us a little bit about your background and how you kind of got to where you are? And if somebody, really wants to have that asteroid named after them, what do they have to do as far as studying and working on that?
Yeah, so I mean, I don't know. I think if you want an asteroid named after you, have to know at some level the right people and not get them pissed off at you for a long enough period of time. Okay, but to work in this area, I mean, I've already been fortunate to have the opportunity to go from, someone really as a kid, sort of completely fascinated by the space program. I was pretty young. But I'm still older than you guys. But yeah, I remember very dimly, the moonwalk and all that. And that sort of sets your whole expectation. It's like, oh, well, this is clearly possible. It's not like, putting a man on the moon is not, it's, yeah, we can do it. It can be done. So it was that during my childhood that gave me an interest. And then when I went into, I studied engineering because it seemed to make sense to me. And I sort of got into, started taking some advanced classes in orbit dynamics, astrodynamics, and celestial mechanics. This was just how things move in space. And for me, it was just completely fascinated by it. And I decided, I'd like to keep on studying this. And I was able to go through, get a PhD. And then I've had a lot of fortune to be able to work at NASA centers, to work in universities, teaching students about all these topics, sort of sharing my interest with them, working with researchers, with PhD students to, hopefully have them go off and do their own contribution. So yeah, it's at some level, it's been something I've always been interested in, but I've also had a lot of fortunate circumstances that have allowed me to continue and to keep on going deeper and deeper into these topics.
And I imagine that's a lot of do your math homework, do your science homework, do your physics, that sort of thing.
Yeah, to treat it seriously, at least. And, I wasn't, it's amazing, if you keep on trying, how things will come to you eventually. Because some of those topics are really hard for me, but when you do them enough, and you commit yourself to it, eventually you get your own insights. And, especially if they were hard for you, if you keep at it, when you do have your insights, they're going to be unique from other people who just, get it all. So it's that's a lesson that you should just always keep trying.
Well, and that seems like, an important part of, we talk about, diversifying the sciences and getting more people, that wouldn't otherwise, you would, when you think of science, you wouldn't otherwise think of, certain people to, be a part of that group. But it sounds like with the more ideas you have coming in, those insights for different people that had different challenges, then you're just building this huge wealth of, of perspectives and backgrounds and experiences that, it all kind of adds together to be this kind of amazingly, I almost want to say like elegant force. Like it all just kind of comes together and you have all these different little pieces. And it seems like that, that's a great argument for, among others, why, it should be, super encouraged and pushed to have more, diversity and inclusion in the sciences.
Yeah, and I think that you're right on with that. I mean, science really all human activities are human enterprise. And as we, if we try to idealize them and impose our own structures on what it should be, a lot of times we end up shaving off a lot of very useful material and perspectives and insights in our drive to, sort of control the narrative. And if you open it up some or a lot, and let people be people and let them be engaged with it, I think we can achieve a lot more. I don't want to call us ants, but think about fully functioning ant colony. Everyone has a thing that they're doing, and they're all contributing in some way. Oh, they're all ants, right? We're all humans. If you step back far enough, we just look like a bunch of ants, right? But we all have our own little tasks, our own thing that we can do. And when we work together and value each other's contributions and inputs, it makes us, I think, a lot stronger.
Very well said. I like that a lot. So we don't want to take up your whole afternoon or anything, so we're going to go ahead and kind of wrap up, but we do want to ask you the final question that we always ask people. Is one of my favorite questions. Do you have any particular asteroid or small body misconceptions that you would like to address or clarify or set straight?
That people have about these small bodies?
Yeah.
Well, I think I already mentioned one of the big ones earlier, the whole Star Wars picture of the asteroid belt. Okay, that doesn't hold true. I think one interesting thing to realize is, and there's one asteroid in particular I'm thinking of. It's called the asteroid Itokawa, and it was visited by a Japanese spacecraft, and I was involved with that mission and very busy with that. This guy is just a couple hundred meters across. Okay, it's tiny, not even a kilometer. Okay, it's up in space all by itself, and you just think, well, it's just a pile of rocks. Nothing ever goes around it. All right, but we go there and we start to study it, and we realize that that little chunk of really a gravel pile up in space has its own seasons. It has its own geophysics. It has its own processes that happen on it. Very different than the ones that we know, okay? But none of these bodies are really static. They're all changing over time. They're all evolving. It's not just a bunch of fossilized things, especially in the inner main belt. There's a lot of active processes that go on. So these are not dry, cold, completely dead worlds, but they actually have their own seasons, their own processes, their own geophysics, earthquakes, this, that, and the other thing. And I just think that's sort of like a very nice perspective to have in your mind.
That is nice. Yeah, you think of, oh yeah, Itokawa, that pile of rocks, and then you learn, wow, it's alive. In the sense of it's changing, stuff's going on, and it kind of adds some inspiration to what you do and what astronomers all over the place are doing, which is studying stuff that might appear to not be doing anything, and then you get closer and you realize there's so much going on right there that we could have never predicted or asked about before we got there.
Exactly. This is part of that microscope. You zoom in,
right,
and you see things that you would never have imagined.
Very cool. Well, Daniel Scheeres, Dr. Daniel Scheeres, thank you so much for being with us today on this episode of A View from Earth. I don't know if we ever actually told you, that's the name of our podcast, by the way. When I first reached out, we didn't know it. Now we do. It's A View from Earth, because we're looking out into the solar system from here on Earth with experts like yourself. So thanks so much for joining us, being with us today, and hopefully we can chat again in the future.
Yeah, well, Colin and Tara, thanks so much. Great questions, and it's always great to talk about these things. So thank you very much for having me. Be happy to talk to you again.